Hello students, in this video we'll discuss the inversion of the discrete Fourier transform. Let's recall that we're working on the L2 space. Recall on L2 of Zn, we have an orthonormal basis. Phi 0 through phi n minus 1. And what do we know about these basis elements over here? Where phi k of j is equal to 1 over the square root of n times zeta to the zeta to the kj. And here zeta is a primitive root of unity, e to the 2 pi I over n, right? That was an orthonormal basis. And that allowed us to write any z in L2. Z is really just the sum. J goes from 0 to n minus 1 of z with phi j, like that. That's our orthonormal basic expansion. Those are our coefficients. Now, these are not exactly the Fourier coefficients. We defined a slightly different variant of these things. We said that from this we got z hat of k was really the sum. J goes from 0 to n minus 1 of zj, and then zeta to the negative jk, zeta to the negative jk, which was exactly, if you put this in complex notation, this will be the sum. J goes from 0 to n minus 1. Zj, and then e to the minus 2 pi I jk over n. And these were the Fourier coefficients. Now what I'd like to do is I'd like to write this in matrix form and see how I can do inversion of this, right? So in matrix form, what does this become? This becomes the following. It becomes z hat 0 all the way down to z hat n minus 1 is this matrix over here. The zero mode is easy to do. All those are zeros. And then over here we're going to have a zeta to the negative 1, zeta to the negative 2, zeta to the negative n minus 1. The next row would be a zeta to the negative 2, zeta to the negative 4, all the way down to zeta to the negative 2 n minus 1. And all the way down to the last row should be zeta to the negative n minus 1, zeta to the negative n minus 1 quantity squared, right? Applied to what? Applied to z0. All the way down to z n minus 1. So we see it's a linear operator. So I'm going to call this mapping over here, I'm going to call this Fn for that Fourier matrix over here. So we really have that z hat is Fn times z. So I want to figure out how to do inversion of this thing over here. Right, so how do we do the inversion formula? Well, what can we notice? We can notice now that if I want to extract these things over here, this has a root n. So if I pull the root n out of that, we can conclude over here that z is really equal to what? It's really 1 over n. The sum, j goes from 0 up to n minus 1. And let's say z of k, for instance, z at point k, is going to be what? Is going to be z hat j, and then zeta to the power what? And then zeta to the power jk over here. Just by this representation, by pulling out a root n over here and a root n over here, we get exactly this formula. And so this basis over this 1 over n, these zetas is going to be the Fourier basis. So in other words, this is not an orthonormal basis, it's an orthogonal basis, right? So if I look at 1 over n, then the function just 1 over n, zeta to the power 1. So zeta to the power 1. Yeah. Let's write like this actually. So let's save ourselves a little bit of writing by doing this. We can define f lk, just to be 1 over n zeta to the lk for k equals 0, 1 up to n minus 1 is the Fourier basis. Okay. And so this representation over here gives me a way of representing the function z in terms of the Fourier transform. And so we see from this that if we define, using this relationship over here, this basis representation, what we can say is we can now say that what? I can now say that if I define w anti-check of k to be what? To be 1 over n, the sum, j goes from 0 to n minus 1, just of w of j times zeta to the jk. Then if I do this, if I plug in the Fourier transform to this, what do we get? So using this relationship over here, we automatically see this relationship over here together with this relationship over here. It gives us our Fourier inversion, right? This tells me that if I did z, let's say z over here, z hat check of k, that z hat check of k is exactly going to be z of k for k equals 0, 1, up to n minus 1. And that's beautiful now, because what that gives me is that tells me that if I want to find the inverse of this thing over here, then to find the inverse Fourier transform, all we need to do is the following. I can therefore write that z is equal to Fn inverse of z hat, by putting the inverse on the other side of the relationship. And from this relationship over here, I know exactly what the Fn hat inverse is. So Fn, the inverse of this matrix, Fn inverse, is just going to be 1 over n, the complex conjugate of the original matrix over here. So there's a factor of 1 over n in our relationship, so that tells us over here that z is equal to 1 over n, Fn complex conjugate. That's exactly just this formula right over here, Fn conjugate of z hat. And this is the Fourier inversion formula. So this is Fourier inversion, discrete Fourier inversion. So as we'll see, we're going to study these matrices more in further videos, or these Fourier matrices, and figure out how, if I want to, if n is a different power, if maybe if n's like half of, twice as large, something like this, I can use sort of block diagonal structures to find efficient ways of computing the Fourier transform and the inverse Fourier transform very, very efficiently, called the fast Fourier transform. So we're going to study this matrix in depth in further videos, but it's important to know that we get a very, very nice structure for the inverse matrix, which allows me to do Fourier inversion very quickly. Thank you very much.